In this particular unit about energy, we're not just talking about the change of energy or enthalpy of chemical reactions, but we're also going to talk about how certain substances will change phases from solid, liquid, and gas, and vice versa, and the energy changes that requires. So just as a quick review, remember that if we have, for example, this reaction right here where we have hydrochloric acid, and we're going to add 16 kilojoules per mole of energy. What we're going to do is we're going to convert that from a liquid, as you can see right here, into a gas. That would be a change of state, which is a physical change. And the way that it occurs is we're going to overcome the intermolecular forces that's going to hold the molecules together. So when we change states, liquid, gas, or solid, we're basically changing the interaction between those neighboring molecules, whether they're being held together very fairly rigidly like a solid, or kind of loosely where they could flow past each other like a liquid, or where they're having very minimal interactions whatsoever as they fly by each other, which of course would be a gas. Again, what we're talking about is the intermolecular forces between them. And again, we're not really changing the identity of the substance, therefore it is actually still a chemical change. On the other hand, down here, the next one we have is liquid hydrochloric acid. We're going to add a whole lot more energy. Notice this is only 16 kilojoules. This is a 431, so that's a whole lot more energy. What that's going to do is it's literally going to break the molecule in half. We're going to be left with hydrogen gas and chlorine gas. Now that again is a chemical change because we're changing hydrochloric acid into hydrogen gas and chlorine gas. Again, those are completely different things. And the reason why what happens, excuse me, when we add 431 kilojoules per mole of energy is we're going to break the covalent bond, not the intermolecular forces, but the covalent bond that's actually holding the molecule together as a single molecule. So I hope that makes sense to you, because again, those are fundamentally very different processes. And what we're going into now is more of the first one, where we're talking about the physical changes and overcoming the intermolecular forces which hold solid, liquids, and gases in those particular phases, okay? So as a quick review, let's talk a little bit about some more of those intermolecular forces. The first one we're going to talk about is London dispersion forces. Again, that's attraction from the it's a very transient, very short-lived interaction between neighboring molecules or atoms. They form what's called a dipole or an induced dipole, and that depends on the masses of the atoms. Okay, again, this can happen between anything and everything. Yeah, and again, it says like here, London dispersion forces are the only intermolecular force between non-polar molecules and noble gases. You remember that noble gases do not make chemical bonds, but they can have a short-lived fleeting intermolecular force, or London dispersion force to be more specific, between neighboring molecules. So they can kind of interact with things, but they're not going to form a true chemical bond. Okay, moving on. What we have next is the dipole forces. Okay, so dipole forces, again, are attraction between the nucleus, the positive nucleus of one atom with the negative electrons of another atom. Okay, so if I could draw this really quick, just to remind you guys what it looks like. So say we have a nucleus here, that's my nucleus, it's positively charged, and then my electrons normally would be pretty much evenly spaced around like so, right? Well, when we put another atom nearby, here's my nucleus, here's my electron cloud with my 2 electrons there. Well, what's going to happen is that for a very, very short-lived period of time, the interaction between the nucleus, it's going to look more like this. The electrons will kind of get away from these electrons, and there will be an attraction between the nucleus of the atom on the left with the electrons on the atom to the right. Again, then these will move away because they, again, don't want to get too close to those. That doesn't last very long at all. Again, this is a dipole-dipole. They're both dipoles, which means, again, two poles, a positive and negative. And again, it happens so very quick and breaks, to use that word. I don't know if breaks is really the right verb, but goes away equally as fast. So that's called a dipole-dipole. The next thing we're going to talk about, again, is the hydrogen bonds. These are super important bonds in biology and in some chemistry. Basically, they are between molecules containing, of course, hydrogen and another molecule which contains nitrogen, oxygen, or fluorine. So if one molecule has a hydrogen and another molecule has a nitrogen, oxygen, or a fluorine, it can form a hydrogen bond. Now, a hydrogen bond is an intermolecular force. Sometimes it's kind of referred to as an actual chemical bond. It's not exactly correct. You might remember these from biology because this holds the nucleotide bases together in a double-stranded DNA. Again, they're much weaker than a covalent bond, so they can be broken much more readily and much more easily. And they also reform spontaneously. It's just an interaction between the hydrogen of one and a neighboring nitrogen, oxygen, or fluorine. Very, very important weak interaction for life. Equilibrium is a word we're going to see a little bit more coming up. Equilibrium basically is a state, and I don't mean a phase, I'm not talking about solid, liquid, or gas, where there is no net movement. Again, oops, I'm talking and writing at the same time. No net movement, that's the key word. Of a reaction in the forward or reverse reaction. Okay, so we've talked about the word net before, and you remember that doesn't mean that nothing is occurring. If there's no net movement, that doesn't mean that everything is completely stationary and there is no movement whatsoever. But the way we often show equilibrium either is a double arrow like this, or like this, or if we want to get all stylized, we can do it like this. Basically, those are three ways of showing that the reaction can go both ways. And when a reaction reaches equilibrium, it is actually still going both ways. It's just that it's equally going right and equally going left. It has reached a state where it is thermodynamically stable. The reaction to the left and right is just right, and there's going to be no more net movement, meaning there's no overall change in movement. But that doesn't mean, again, that there's no movement. There is still reactions going forward, there is still reactions going in the reverse direction, but they balance each other out. And therefore, in the grand scheme of things, there's no more change in the reaction going forward and backwards because they balance and cancel each other out. That's, again, what is called equilibrium. All right, going back into the changes of phase, let's talk a little bit about each of them in more specific detail. So, for example, you're all aware of something called evaporation or condensation. They are basically, for all intents and purposes, the exact same thing, but they're just going in the opposite direction. What I mean by that, if we are evaporating, we are going to start with a liquid, right? We're going to add a little bit of heat, the HV, that stands for heat of vaporization, little sub V stands for vaporization, so that's heat of vaporization. And if we add heat to a liquid, we would eventually get a gas, right? Now, again, that would be an endothermic process. We're going to add heat. Notice heat is on the left side of the arrow, so we're adding it to the reaction again being the arrow itself. And we're going to end up with the gaseous phase of that particular compound. Again, looks a lot like this, right? On the next example, we have condensation. Condensation, you are starting with a gas, and you're going to end up with a liquid and release some heat. Notice heat, the vaporization is on the right side, therefore it's being released, therefore it is an exothermic process. Remember, this is not a chemical reaction per se. We are just changing the states of matter. Again, this is a physical change, right? We're going from, say, liquid water to water vapor or vice versa. It doesn't have to be water, I'm just saying. So evaporation occurs when molecules on the surface of the liquid have enough speed, or I'm going to say kinetic energy. Squeeze that in there. Sorry about that, guys. To separate from each other and enter the gas phase. So what that means is the kinetic energy of the molecules in the liquid has to be sufficient and great enough that they could basically break the intermolecular forces, holding them as a liquid, and then speed off into the gaseous phase up into the air above it, right? If it doesn't have enough or sufficient kinetic energy, it's just going to vibrate and oscillate and stay where it is and flow past each other because there's still strong enough intermolecular forces to hold it in the liquid phase, okay? Now, there are some liquids that are called volatile or volatile, some people will say, and they evaporate very, very quickly. Very quickly. You are familiar with some of these. We just don't typically use the word volatile. They have very weak intermolecular forces, which is why they evaporate so quickly, and have greater vapor pressure, which is not surprising if you think about it, because if they evaporate easily, then they're going to go into the vapor state or the gaseous state. Therefore, the vapor pressure, because there's so much of it going into the vapor very, very easily, the vapor pressure will be quite more substantial than, say, something that is not as volatile. Some examples of these would be things like gasoline. You know how gasoline, it smells so bad, right? You spill it on the ground, or even worse, you spill it on your shoe. Oh, it stinks so bad, right? The reason why—
Angel Espino, if you are still in the building, would you please come to Ram Central to the front of the building? Thank you.
Hope you guys got that. So the reason why it smells so bad is because it doesn't stay in the liquid state on the floor or wherever. It's actually going to volatilize, which means it's going to evaporate so quickly, and therefore it's going to go up your nose and you're going to smell it really, really strongly, right? Other things are like acetone. You guys all know, like, for example, fingernail polish remover. That stuff stinks. And the reason why it's so strong is because it's volatile and it evaporates very, very easily, very quickly. A couple other things are some forms of alcohol and chloroform, which has a very distinct scent to it. Okay, those are all very volatile substances that evaporate very quickly. If you were to accidentally spill gasoline on the floor, it'll evaporate very quickly and it's gone. Ironically, that's one of the worst things you could do, because gasoline going straight into the atmosphere is actually much worse than combusting it, which is a little odd. Examples of non-volatile samples or substances would be things like water. Water does evaporate, but it's pretty dang slow to evaporate, right? Or other sort of solutions. For example, if we had sodium chloride solution, aqueous, then that's going to evaporate very slowly as well, relative to the volatile substances. Now, what boiling is, which again is kind of a way of saying evaporation, is when the vapor pressure is actually going to be forming underneath the surface of the liquids, which is why you get all those bubbles, right? The bubbles come from the bottom typically, and that's because the vapor, which is the gas, is going to form below the surface, and it has so much energy, it's going to go all the way to the top and escape. So that's going to, again, when the vapor pressure equals the external pressure of the atmosphere. Typically, we talk about 1 atmosphere, which again is sea level. If you were high up, say in Colorado, where it's a mile high, or even on, say, Mount Everest, the external pressure is much less. Therefore, it will boil quicker because the vapor pressure doesn't need to get as high. We'll talk more about that later. Okay, moving on to the next phase change, we have freezing and melting. Freezing and melting, again, like I said before, for all intents and purposes, is basically the exact same thing. We're just going in the opposite direction. If we are, let's say if we have a solid and we add heat to it, we would end up with a liquid. Conversely, if we had a liquid, then we removed heat, that would make it a solid. Again, this would be endothermic. This would be exothermic, right? Again, it's basically the same thing. Just notice the heat is on the opposite side of the arrows. Again, this means equilibrium, as you guys know already. Moving on, for sublimation and deposition, you guys probably have been exposed to this at some point, but maybe kind of went in one ear out the other, because we don't talk about sublimation or deposition very often, but they are a phase change and they do occur. They're just not quite as common. So sublimation would be, for example, where we have a solid, we add a little bit of heat, and what we end up with is a gas. We don't even, we completely skip the liquid phase. We go straight from a solid straight to a gas, which is kind of weird, right? Again, that would be Indo because again, your heat is on the left side of the arrow. On the other hand, if we had a gas and we went straight to a solid, skipping the liquid phase, releasing heat, that would be, come on, Pin, that would be called deposition. So that is deposition. Examples of that would be like dry ice. You all know dry ice. What it actually is solid, oops, let me try that again, solid carbon dioxide. So solid carbon dioxide is dry ice. If you put dry ice on a piece of paper, it will go straight to the gaseous phase, which you guys see is that cool, stuff coming out of the dry ice, but the paper will not get wet. Therefore, we call it dry ice because it doesn't get wet. It goes straight from the solid brick form of dry ice straight to gas. To go the other direction, again, is called deposition, which isn't quite as easy. Like it says here, solids with high vapor pressures sublime in air. I think that's what that means. And have weak intermolecular forces. Okay. All right, guys. Again, that's make sure you guys are familiar with sublimation and deposition. Those are two different phase changes. Again, we don't talk about very often, but you do need to be familiar with them. As always, guys, thank you very much for watching.